swing.
Nice. Wait, what changed?
I have no idea.
He killed the other screen.
No, now you gotta count.
Thank you.
Yeah.
Yay!
Oh, sweet.
Okay.
And it says unknown in the upper left hand.
That's okay.
Well, that's okay. we don't know.
That's
We're not
irrelevant.
too specific. So this is a presentation. I titled it Fractals, what they are, how they work, what we know, and what we don't know about them. And this was kind of a tricky presentation for me to put together because I'm working with people who are obviously smart, but people who don't know a lot of background about fractals. I mean, Professor Kisik had you guys raise your hands, and only one person said they knew stuff about fractals. So now I'd like to start off with an insightful quote. You guys feel free to read along. The great book of nature is written in mathematical language. Its characters are triangles, circles, and other geometrical figures without which one wanders in vain through a dark labyrinth. This was said by Galileo. Okay, we all know it's crazy. We knew that this was going to happen. It turns out that what Galileo is referring to are Euclidean shapes, and these are actually completely useless in modeling deterministic chaos and irregular systems, which we're trying to do here, which is very important, we've found throughout the years. So this is talking just completely before fractals were even discovered. So, what are fractals? A fractal is the end result of an infinite process in which a geometric shape that can be split into over and over into self-similar parts is divided, each piece being a reduced-size copy of the whole. And what is important to note about the definition of fractal is it's the end result is a fractal. You can't just say an equilateral triangle is a fractal, it has to be already divided. So that was kind of like a key point in the definition. So how is this important to our class? Well, binomial coefficients for one. We learned about Pascal's triangle, obviously. And I just want to do a quick review, just in case. We know that these are binomial coefficients. We know that this is 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. We know that if we wanted to do a plus b cubed, we're going to end up with 3 things. And they're all going to be this row of coefficients. But, of course, as you guys hopefully already know, Pascal's triangle is not a fractal. Rather, Sierpinski's gasket is the fractal version of Pascal. And this is Pascal mod 2. So does everybody know mod 2? Division?
By now they should.
So it's basically turning all the ones, thank you for answering, but I'm trying to make this a little interactive, a little fun for everybody. We're changing all of the even numbers to zeros, all the odd numbers to 1. And this will actually form, this will actually form the iterations that we know to be Sierpinski's gasket. And if you see right here, these are the self-similar triangles. And this obviously goes on and on. So, before I talk about the algebraic properties of fractals, I want to give you one of the important sort of calculation things for fractals, and that's how to calculate dimension. Dimension is the log of the number of self-similar pieces over the log of the magnification factor. So now I'm going to start off with a pretty easy fractal. We're going to go with a perfect square, what that is. And we will divide it in half. And all 90-degree angles. So the dimension of this would be log of, how many self-similar pieces are there? 4. Yes, 4. Divided by log
1
of, what is the magnification factor? What do you have to do to this square right here to get it to look like this big square?
Divide by 1/4.
Multiply by 2, actually. You multiply each side by 2.
Oh.
So this equals 2. Yeah, that's okay. We all get that wrong every once in a while. So, perhaps the most simple idea of a fractal would be a line segment, because you could divide this in infinitely many pieces, and each piece will be a replication of the whole when multiplied. So the dimension of this, let's see, It would be log
4.
So this will be a one-dimensional, and everybody agrees that a line segment is one-dimensional. Okay. So now we're done with the easy stuff. I just had to get you guys a little warmed up to thinking. We're going to talk about the algebraic properties of the fractal. Now a lot of questions come into play, even today. We don't really know if fractals have algebraic properties like the other things we've studied. We don't know if they operate with the same rules. And what I'm going to talk about is what's all this business about Fn. And this will hopefully answer the top 2 questions for you a little, although stuff is still being discovered. So Fn is the number of ones in the first n rows of Sierpinski's gasket. So we have this right here. I think I'm going to draw it a little smaller really quickly because it'll be easier to picture. We're going to put Fn right here. So we're going to have, obviously, 1, 1, 3, 5. I mean, you're following this. So the formula for Fn is actually the sum from k equals 0 to n minus 1 of 2 to the b times k. Okay? And b of k is, or b times k is the number of ones in the binary expansion of k. So, to picture this, we're going to have k, we're going to do bk, and we're going to do 2, 2. Now k is, we're just going to number the rows, but we start, remember, with the 0th row, and then we go on. Okay, and bk would be the number of ones. So, in the binary expansion of 0, 0 in binary is still going to be 0. So there's none. 1 in binary. 2 in binary.
10.
3 in binary.
2.
Exactly, because we're counting the number of ones in 10. From 1, 0, as you should say. Okay, so 2 to the bk will be, just kidding, 1, 2, 2, and 4. Now you're thinking like, okay, this is all well and good, but what is this going to represent? And Fn actually tells us what the length of the curve of each triangle is going to be, because if you notice, the O's, the zeros represent the triangles. So what we have outside are the perimeters, and some people actually draw this as dashes, each one representing a side, to create these lengths. And this Fn can be followed over time. So this is basically giving us the rate of change over time of the curves of these triangles, of the fractals. But that would insinuate that these can be derived, right? Because if you have the rate of change over time of something, isn't that just the derivative? Okay, well, keep that in mind because I'm going to reference back to that. But to take Fn a little further, now we did our dimension up here. So the dimension of Sierpinski's gasket, which I always draw upside down, and I don't know why. I want to start with like the middle part. When we remove this middle, there are three self-similar parts, and we multiply each side by 2 to get it back to the original length. So the dimension of this is log 3 over 2. Now, it has been conjectured that theta, if you call theta log 3